Good morning, sir. Are you able to hear, sir?
Sir, you are in mute, sir.
You can kindly unmute.
Hello.
Yes, sir.
Okay.
Yeah, good morning. Good morning.
So the second day of the FDP program is going to start now. I welcome all the participants back who had attended it yesterday and have come back for the today's session. I indeed feel very privileged to introduce our today's speaker who is going to speak on MIMO and cognitive radio for sub-6 gigahertz 5G applications. So the speaker, I would like to introduce Dr. Raghavendra Kumar Chaudhary, who is an assistant professor of the Department of Electronics Engineering, Indian Institute of Technology, previously ISM Dhanbad, India. He received his BTech degree from UIET Kanpur, India in 2007 and the MTech degree from IIT BHU Varanasi in 2009 and PhD from IIT Kanpur, India in 2014. We welcome you, sir, for today's session.
Thank you.
He has researched in developing the metamaterials antenna and dielectric resonator antenna, DRA, and his main work is development of the circularly polarized compact antenna is one of his major area of contribution. And his current research interests include MIMO and cognitive radio, circularly polarized DRA, reconfigurable metamaterial, metasurface for antenna and observer design, and frequency reconfigurable active array antenna with beam steering. And to his credit, he has published over 95 papers in the top work is development of the circularly polarized compact antenna. Currently, he has one of his major students working under him. And his current research interests include MIMO and cognitive radio, circularly polarized DRA, reconfigurable metamaterial, metasurface for antenna and observer design, and frequency reconfigurable active array antenna with beam steering. And to his credit, he has published over 95 papers in the top work is development of the circularly polarized compact antenna. Currently, he is one of his major area of working under him. And his current research interests include MIMO and cognitive radio, circularly polarized DRA, reconfigurable metamaterial, metasurface for antenna and observer design, and frequency reconfigurable active array antenna with optical beam steering. And to his credit, he has published over 95 papers in the development of the circularly polarized compact antenna. Currently, is one of his major areas of propagation. And his current research interests include MIMO and cognitive radio, He has also circularly polarized DRA, reconfigurable metamaterial, metasurface for antenna and observer design, and frequency reconfigurable active array antenna and I hand over to beam steering. To his credit, he has published over 95 papers in the development of the circularly polarized compact antenna. Currently, is one of his major areas of propagation. And his current research interests include MIMO and cognitive radio,
He has organized each new mic on the participants continuously by this company. Today I'll talk over MIMO and cognitive radio for such gigahertz telepathy application. So very good introduction already given by the organizer. So let me introduce some of the facts about how my work. This is the building where we are doing the research related to all these things. And these are the instruments we in our lab we have almost all the instruments to carry out the research related to 5G and compact antennas. Now coming to the research group, so the area of interest already told by the organizer, and these are my PhD students, full-time PhD students, and these are the graduated students. And then my lab is sponsored by the different funding agencies like DRDO, ISRO, SERB, TCube, and my own institution. So coming over the outline of the presentation, so I'll introduce with the 5G. Then after we'll try to learn here that why the MIMO is important. Then we'll compare with the existing one with the MIMO. And there's one of the very important thing is isolation in MIMO that I'll try to explain in detail. And then after there are some work actually done in our lab, and we publish those work, that's published paper. I'll try to show here that what actually we perform. And then after I'll show the cognitive radio, what is the cognitive radio and what is the importance in MIMO actually, how we integrate the MIMO and cognitive radio for 5G applications. And then after the research work on cognitive radio and MIMO, which we recently done actually in 2019 and published, and then followed by conclusion and references. So let me start with the motivation, because without motivation it is really difficult to do the things. So this picture actually, if you see this picture, this picture is self-explanatory already. So if you see nowadays the Internet of Things is very famous, and it touches our life, every aspect of our life. So we can see here this we are thinking about the smart homes, we are thinking about the smart vehicles, smart cities, smart schools, education, and healthcare. So everybody, the backbone is internet, and if your internet is sufficient and very fast, then you can expect all these applications with the help of this IoT. So the thing is, the motivation is that we have to somehow increase the speed, these things, the data rate actually. So the thing is, this 5G actually comes into the picture, and I believe that you have seen in news also, and many magazines also, that the trial is going on. So let me talk over the 5G or 4G actually. The 4G actually we are using, and it is well justified if I compare with the 4G. So this is the photograph you can see I have taken from this magazine. The link is given. You can also read in detail. So there are 8 parameters over that the 5G actually is compared over the 4G. So the first is the latency. So if you see the latency, this is less than 1 millisecond. So why this is important? So low latency is required for the time critical application. For example, like connected ambulance, correct? To transmit the health data, including video stream, the remote diagnosis, etc. So for that actually, if latency is low, it is really very good. So particularly we can improve the medical services. It's remote medical services, correct? Then after there is a device density. So if you check the device density here, this is greater than 10 lakhs per kilometer square. If I explain this thing, this is high device density is needed for constant data collection and the transmission of the network. Critical real applications such as automation driving. Nowadays you have seen the Tesla car. You have went through this Tesla car and seen the video actually. So this is automatic driving and all the things, and it requires so much accuracy actually. So where the device density is needed. Then after we're talking about the data rate, this is close to 10 GB per second. And then after area traffic capacity, this is around 10 GB per second per kilometer square. So, and then after we have the low consumption. So low consumption is really needed, correct? Because nowadays everything we want to keep in pocket, and battery life should be improved. Definitely we have so many options in power actually, like battery, lithium ion battery, and still the research is going on, and hopefully the things will be improved. But the thing is, if we try to improve the technology what we are using, we can also save the power. So low power consumption is the ecological and your economical importance, correct? Now coming over the bandwidth, bandwidth is one of the area actually where we need to these things we require nowadays due to number of application. So the this high bandwidth forms the basis for the support of modern technology, like it necessary to meet the requirement like broadcasting and video conferencing. And then after spectral efficiency, if you see the spectral, I can say this is BPS 30 BPS per hertz. So high spectral efficiency enables more efficient use of transmitter sites. For example, allows network operator to offer the data packets at the lower prices. And then after we want the high reliability. What is that? So high reliability along with the low latency is a high traffic capability is necessary. For example, like a smaller safety distance from the autonomous vehicle. Correct. So these are just some points actually which motivate to us to do research over the Python. Now, coming over this picture, actually, this is really very important to understand, and a lot of debate has happened in the past. And if you see in a social media, so many article, you might have seen that 5G all related thing is not good for the health. So let me clear the picture in a scientific way, actually. So, like up to up to millimeter wave, the waves actually is non-ionized radiation. So this is not going to damage the DNA. Whereas if you go beyond these things, visible light, like X-ray, beyond the visible light, X-ray, gamma rays, definitely it is ionizing radiation and it can damage the DNA if the continuous exposure will be there. So definitely we are safe, I would say, but we have to control the power. So power is another phenomena. Like if continuously, if the things are exposing, it is going to damage. So both the things actually, but we have to handle the things smartly. Now coming over the spectrum actually. So if you see, particularly our research group at IIT ISM Dhanbad, we are working for sub 6 gigahertz. We opted sub 6 gigahertz. The reason is the cost and these things, because if you talk about the infrastructure over the sub 6 gigahertz easily available in the market. So better, we thought better to improve first at sub 6 gigahertz. Then after we'll move to 24 to 28 gigahertz window, and we'll try to improve in millimeter waves. So parallelly we are doing on a millimeter wave also, but in this presentation I'll explain sub 6 gigahertz, and these are the bands actually opted by several countries, and I hope in India also we will see within this frequency range, which is 3.4 to 3.8 gigahertz. So this is introduction to 5G actually. The thing is, if we compare the sub 6 gigahertz and millimeter wave actually, so we can divide in terms of the technologies involved as well as the advantages. So the technologies involved in a 5G is a MIMO, then cognitive radio, massive MIMO. Whereas technology involved in the millimeter, if you find the MIMO is common, and some three new things you can see: the phased array, beamforming, and side array. So we need to club all four to get working at microwave frequency. And here also we are introducing the combination of MIMO and cognitive radio technology. So so we can improve the data rate, and smartly we can handle the spectrum actually available. Coming over the advantages, so the thing is, like here at sub 6 gigahertz, the frequency is small as compared to the millimeter wave, so we can expect the good penetration, correct, and it will be going to longer distance, correct. And the big thing is the cost. Infrastructure is already available up to 6 gigahertz in the market, so we need not to worry these things. And then after, if you think about this millimeter wave, correct, so definitely high data rate is there, correct, low latency is there, and there are large unlicensed spectrum we can utilize there, correct. So bandwidth issues, no bandwidth issues. But the thing is, infrastructure is one of the problem, and if you see, so the infrastructure is costly actually. But still, the things are working, and hopefully, when the technology gets cheaper, and it would be easily available to the common people actually in future. So the trials are going on, and if you see the trials, particularly this is at sub 6 gigahertz, and other trials are also made on the millimeter waves. Correct. So coming over the free space path loss. So this is the equation actually. So if you calculate the path loss at 30 gigahertz, so this is 23 dB more than 2 gigahertz. So you can see that there is a huge amount of loss involved when we are working in millimeter wave. So that is why I'm saying the infrastructure is we have to develop actually infrastructure at this frequency. So so let me start with the sub 6 gigahertz because this is our area of interest actually. So here you can see in this picture, this is a MIMO antenna, and this is a cognitive radio. The idea of the cognitive radio. So what we are going to do, the MIMO is well known, and still we are using like the 4th generation actually. We are get benefited from the 4G with high data rate and all the things, and this online classes and all the things. So 4G is still providing these facility actually. But the thing is, in 5G actually, what we are expecting that because cognitive radio, which allows to us how smartly we can use the unused spectrum. Correct. So if we are combining these two, MIMO and cognitive radio, so we may expect that application for the sub 6 gigahertz 5G. So this is the area we focused actually, and we developed some antennas over there, and we tested and we found okay, these things so we can use this. Now, if you talk about the importance of MIMO, so there are a lot of things actually coming in the picture because MIMO is not a new area, I would say. Correct. MIMO is matured area, I would say actually, and further this could be used as a tool to improve the things in near future. Correct. So let's discuss some of the facts on the MIMO actually. Most of the communication people having these communication people background, they already know about the MIMO. For the antenna engineers, it may be sometime new, but they are knowing, I believe. So the thing is, there is a one thing which is we call as the diversity schemes. Correct. So what is that? This is diversity schemes actually refers to a method to improving the reliability of a message signal by using two or more channels. Correct. With different characteristics. So diversity actually mainly used in the radio communication and common technique for combating fading and co-channel interference and avoiding the error burst. So here you can see this thing diversity scheme can be used to increase the channel capacity. And the channel capacity is the upper bound of the data that we can achieve. And there is another important point is that data rate should be smaller to channel capacity for error-free communication. Now coming to the diversity scheme, so we have the three things, correct, as an antenna engineer. So I will be talking about the antenna diversity. So there are the other two things, which is the time diversity and the frequency diversity, correct. So the thing is, our focus is here that how to do the diversity in antennas particularly. So there are two things, which is the spatial and the polarization diversity. So spatial diversity, there are the certain scheme like CMO, MIMO, MISO, and MIMO, correct? And polarization diversity is that we supposed to control the polarization of the antenna. And as an antenna engineer, definitely we can do these things, correct? Now, coming to a real-time example here, correct? So you can see a camera here, and on the top of that two antenna actually, and the angle between these two antenna is 45 degrees. And this camera is shooting some event actually, you can see. So here, this is the very good example of the polarization diversity, because the thing is you place the things at 45 degrees. Now coming over the different scheme, which is CISO, single input, single output system, then CMO, which is single input, multiple output, MISO, multiple input, single output, and MIMO finally. So the thing is, first CISO will provide no diversity, and then CMO actually provide the receiving diversity, and the MISO is provide the transmit diversity. Because here we have the option in the transmitter side, where here the option is in the transmitter side. Sorry. So here, if you see the MIMO, actually here you have a diversity in both the sides. So why this is important, I'll explain in the coming slides. Correct. So let us try to understand these things from this slide actually. This is somewhat important, and for those who want to work in antenna, particularly MIMO, they should understand what are the importance of this diversity schemes. Correct. So here you can see here that we have taken here the CISO, and we given the formula to calculate the channel capacity for LOS communication, line of sight, and this is non line of sight communication, which is a critical scenario, and we're supposed to focus over these things. So, and this is the channel capacity for single input, multiple output. Now here you can see the picture actually. So this is for single input and multiple output. So for example, we have taken the two antenna at the receiving side, and you can see there's a two paths here. Correct. There's a two path, and these are the obstacle you can see. So the thing is, when the signal is coming out from the antenna, actually transmitter antenna, so definitely it is going to interact with the surroundings. Correct. So let's say that this is the path 1 and this is the path 2. Actually, the signal is reaches to the antenna 1. Correct. So the thing is, like here, as I told you, see the channel capacity, and what is this rho r? Rho r is actually SNR, signal to noise ratio, and the PT is here your transmitted power, and sigma square is the noise power. Correct. So for practical scenario, we come across the non-line of sight. Correct. Correct. So non-line of sight is for the textbook item is good to form the understanding. So in non-line of sight communication, the same signal will undergo different multipath before it reaches to the receiver. Correct. You can see here, if these multipaths signals having the same information add destructively at the receiver, then H square become 0. When the H square becomes 0, actually this channel capacity will 0. Correct. For this. Correct. So so what we can say, then the communication will fail actually, because data rate should always be less than the channel capacity for the error-free communication, as we talked about the previous slide. Now, in the scenario when mod of H square is 0, the diversity scheme is important, and we should rework actually how we can do the things. So coming to the CMO, single input multiple output, you can see if we use the antenna diversity, correct, like let's say CMO, correct, there is two antenna, correct, using the antenna 1 and antenna 2. So at the receiver side, so hence what will happen, this channel actually we can write as H11 square and H21 square. So the thing is, let's say if for the antenna 1, if you are losing the signal, and luckily you are getting this the things at the antenna 2, so the thing is definitely H11 will be 0, and here but H21 you are getting something, so it formed the channel, and definitely some channel capacity will be formed. So here we can find the importance of this diversity. So if we have the multiple of antenna, the chances of getting the signal is more actually, and the communication would be proper. Correct. So this is the idea about the diversity. Correct. Now I have listed certain formula actually. These are from the textbook. You can easily find channel capacity of the different schemes. Right? So you can see here particularly MIMO will offer you number of option H11 square, mod of H12 square, like that. Correct. So coming over these things, so let us try to understand MIMO once again in the spatial diversity and the spatial multiplexing. Correct. So one improve the reliability and one improve the data rate. Correct. So here you can see our data actually the data is going to transmit from the 3 individual antenna, correct? And let's say one bit is taking 1 second to transmit, correct? So the data rate will be what data rate will be, these things is pretty high, 3 bit per second, correct? So so the thing is, like, if you check here, like a single data actually is fed by the individual antenna 101, correct? So let's say this again, this is 1 second per bit. So here the data rate, here the data rate will be this 1 bit per second, and here this is 3 bit per second actually. So in this way, the data rate will be increased actually. So that is why the things we can, means this particular fast scheme, if you see, this improve the reliability, means we are sending the same signal from the 3 individual antenna, whereas here if you see, we are sending the signal in a parts in a 3 different antenna. In this way we can improve the data rate. Here we can improve the reliability, correct? So this is the thing actually. This is one of the example I have taken. If you see, so here I try to explain that how the data rate actually will be increased actually in MIMO system. So the thing is, if you see that, let's consider here, this is a mesh, you can see this. This is 100 megahertz channel bandwidth, correct? So I consider here from 0 to 100 megahertz. So let's say for the easy explanation, let's divide, correct, this 100 megahertz bandwidth in 10 sub channels. You can see this is a 10 sub channels here, with each sub channel getting 100 megahertz by 10 means 10 megahertz bandwidth. So it means that each sub channel can carry 10 m symbols per second, correct? So that means each symbol from each sub channel will take 0.1 microsecond, correct? So because we have the 10 sub channels, so in an entire channel we can say that 0.1 microsecond, correct? The entire channel can be transmitted 10 symbols. So finally the data rate in this system, we can say this is 10 symbols per 0.1 microsecond. Now the thing is, for example, let's say this is a data actually, correct? This is the data in this format, and this data needs to be transferred. So here particularly I consider for QPSK modulation. Other higher modulation scheme may also be considered, but for the example I have taken these things. So in which the 2 bits will be combined and form a single symbol, correct? Okay, so these symbols are represented, let's say 1, 2, 3, 4, correct, and so on. So these symbols will be radiated from the antenna and transferred through the channel of 100 megahertz bandwidth, what we discussed actually. So as this from this figure you can see these things here. The data rate is what? This is 10 symbol per 0.1 microsecond. So as we explain these things, so the data rate of 10 symbol per 0.1 microsecond is nothing but what? This is 20 bits per 0.1 microsecond, because here the one symbol is equal to the 2 bits, correct? So so we can write this gets double actually. So the thing is, now if we want to increase the data rate, correct, so I can increase the modulation from let's say QPSK to 8PSK. So the data rate will be 30 bits per 0.1 microsecond. But the thing is, however, this is not the right way actually to improve the data rate, because moving to the higher digital modulation, you know these things, that bit rate will be high, error rate will be high. So how we will do these things, correct? So there is an option here, which a solution actually. So this is provided by the using of MIMO actually, correct? So let's say this picture actually, here we use the 2x2 MIMO. So let's say the 2x2 MIMO system has been here implemented. So the thing is, if you see this figure, sorry. So let's say this symbol number 2 and 4 are transferring from 2 different antennas, but at the same time frequency and time, correct? So even though this 2 and 4 are transferring at the same frequency and time, there will be no interference between them because of this is 2 and 4 are divided in spatial domain. Correct. Correct. So as I already explained this thing, said that no two signal radiated from the two different antennas. Correct. So this elements never follow the same paths. Correct. So that's why the 2 and 4 are divided in spatial domain, and the interference between them is actually low, actually very low. So similarly, these two symbols like 1 and 3, if I talk about, correct, will also do the same. Is using 2x2 MIMO. So with use of 2x2 MIMO system, now the data rate, I would say this things will be 20 symbol per 0.1 microsecond, which is nothing but now 40 bits per 0.1 microsecond. So finally, we can say the data rate actually we made it double using this 2x2 MIMO. Correct. So this is the idea actually by which we can improve the data rate. So coming to the advantage, I have listed this thing. So many advantages are there. I already told so many things. This thing. So spatial diversity mode is one of the things, and the MIMO increase the data rate. We have already seen. Taking an example actually. Then as the MIMO increases the array gain, it more suitable from beamforming operation. Is the things we are doing, and you can see the number of published paper actually, and these are some disadvantages I would say here, because this is a totally active software is very high actually, and we have to carefully design the required construction in terms of ECC and isolation. Correct. So these are the certain things actually. Now coming to the MIMO parameter, so there is one of the very important parameter, which is the isolation in the port. Correct. We know this when we are taking the number of antenna on the same place. Correct. So these antennas element will be talking to each other, and we don't want these things actually. Correct. And how to find this mutual coupling? Generally, at microwave frequency, we are calculating the S21. Correct. S31, S41, like that. Means number of the elements depends upon. So I think is looking at the 15 dB isolation is considered actually for designing these MIMO antennas. So try the things 20 dB, correct? So that because when you do the measurement, there are certain losses and all the things. So you try to fix at 15 dB. So now the thing is, if you try to relate this isolation with total efficiency, this is related by this formula. So if the isolation is high, correct? So you may expect here the total efficiency is going down, correct? And another parameter is ECC actually. So ECC is one of the very important parameter actually, and by these formulas actually you can calculate. And I recommend here you use the second formula actually, because it is derived from the far field radiation pattern. And if you are talking about the envelope correlation, these things, so it tells that how independent two antennas radiation pattern are. It means far field property means how means if these patterns are talking to each other, then there is a problem. So if one antenna, let's say, is completely horizontally polarized and other is completely vertically polarized, so the two antenna would have the correlation of 0. Correct. So means what I'm trying to say, that if one antenna only radiate energy towards, let's say, another is towards zero correlation. Correct. Okay, so this is really very important, and actually diversity gain is calculated again by this ECC, so you can use this all the parameters, these things in detail, so we can skip this thing so that we can see the design of the 5G antenna. This is the TARC actually is very important, like input reflection coefficient. So we have an active reflection coefficient due to the number of elements are presented in your MIMO antenna. Then after channel capacity loss and the value must be this things less than 0.4 bit per second per hertz, correct? So here you can see this is the formula actually, correct? And we related with the S11 because for the microwave engineers, S11 and S21, getting these parameters is very easy because after the calibration and all, you can calculate this all the parameters of the antenna. And once you have the S parameter, you can calculate the psi matrix. And once you have the psi matrix, you can calculate the channel loss. And after that, this is one of the far-field property of which is a mean effective gain. And this mean effective gain is nothing but this is mean received power divided by total mean incident power. And this is one of the formula, this equation 10 you can utilize. I think here you can see the G theta, P theta, and G phi and P phi. These all some papers from the techniques you are for the parameter. Correct. Now the thing is, these 5 or 6 parameters actually what we have seen is really very important. And among all these things, the isolation, one of the very important and start should be the start point. I would say here that we need to take. Correct. So the thing is, let's talk about the isolation. Correct. So as I told you that isolation, we are in microwave engineering, we are calculating with the parameter S parameter like S21, S31 like that. Correct. But how to improve the isolation? This is the question actually. So that question could be answered if we see the literature. So already several research group already proposed techniques actually, and broadly if you see the 5 techniques very popular actually to find it out the isolation. Correct. So these are the techniques actually. Here you can see the isolation could be done with the filter based isolation. Correct. We can include the band stop or band pass filter, so we can stop the surface wave by which the antenna's elements are talking. And then after many of the research group also use the FSS, which is frequency selective surface. And then after many of the research group also told about the DGS, which is defected ground structure they used. And then after there is a one trivial thing I would say actually, this is antenna placement and orientation, because the orientation and placement definitely it will increase the size of your antenna, but this can provide you the solution at the same time. Correct. And finally the reflector base, this is one of the technique actually by which you can improve the isolation. So in our lab actually we use filter isolation, so I will try to on some of the paper actually what we published these things. So this is one of the work actually on the new antenna, and particularly we attempted here that how to improve the isolation. So this work we published in IIT Electronics Letter. Now if you see here these 2 monopole antennas, correct, you can see the 2 monopole antennas are here. And after that what we did, we inserted our bandpass filter. So inserting this bandpass filter will providing that 27 dB distance, correct. So if you see the S parameters, correct. So like for the first diagram when the monopole antennas without the filter is there, so this is the S parameter, correct. So and S21 is like that. So you can see that there is a huge transmission, means these 2 antennas are talking each other. Now what we did actually, we designed the filter at the same band, correct, and we place actually that filter at a particular location, so that those surface current could be stopped at particular band. So here you can see these things, that this is the band pass, this is stop band filter actually we designed, correct. And what we did actually, we placed this stop band filter at this place, correct, so that these 2 things are connected. But when you are connecting these filter or other extra element, definitely the frequency shift and other things will be happen. So in a microwave engineering, so what we are actually doing, we can match the system through some stubs actually. or we can tune the frequency as well by changing its capacitance and inductance. So what we did actually, we included the stubs here, correct? We stubs here, so that what happened, this if you see this result, correct? If you compare this first and fourth results, what you see that now S11 at particular this band 2.6 to 2.8, in between that, if you see, the isolation is very small, correct? And this is the success actually, correct? So once you have the very good isolation, definitely you can go ahead and you can design this things MIMO antenna for the application. And after that, actually, we plotted here the real part of permittivity and permeability, because one of my area is metamaterial actually. So here, what we did actually, we done through the ANG transmission line approach, correct? So we supposed to verify this is ANG. So from this figure, you can see that negative permeability you can see in a small region, correct? So on that claim, we are saying this is an ENG. This is just a cross verification of our concept actually. So finally, we measured these things. We done the fabrication on the low cost substrate, and we found the measurement and simulated results are very close, correct? And then after we did an extra experiment, because nowadays you are saying you are seeing in a literature that vertically or horizontally polarized antennas are gradually being replaced by the polarized antennas. Correct. That's one lose the information. So better to use the CP antenna. But the thing is, with the CP antenna, the bandwidth and other restrictions are there, and this is one of the area where we are working to broaden down the bandwidth of the acceleration bandwidth. So coming to the next these things, so we done some other things further actually with the same student actually. This is my student Srinath Reddy actually. He's working with me as a PhD student. So mainly this boy is actually working in MIMO antennas and this 5G actually. So further, what he designed a reconfigurable isolation enhancement using the filter-based technique. So what is the new in this work? Correct. So I want to explain here. This is a unique kind of thing, because the first time we claimed, this is the first time this in a literature nobody tried actually before. We tried first time that we proposed the isolation between the antenna at the same time the frequency reconfigurability. Why these two things are important? Try to understand, because we want to save the size. Correct. We don't want we want to accommodate all the things in mobile, and finally we want to put the things in our pocket. Correct. So definitely we want to reduce. We have to compact the handle device. Correct. So the frequency reconfigurable things will provide you the extra dimension, so that you can accommodate the two bands within the same structure by incorporating what? By incorporating two bands with the active circuits actually, like pin diode, vector diode, all the things we use of these things, we can incorporate the things within the small size. So let me explain these things and how we perform this thing. This work actually we published in IIT Microwave and Antenna publication in 2019. So this is all the work I'm presenting here. This is one of the recent work and state of art. So audience, the researchers, the students who are working in this area, they can refer this paper and the reference of this paper, so they may get the idea that how to design the thing. Particularly, we use here the HFSS and CST actually these tools to design these antennas. Correct. So this HFSS and CST, you can see a lot of training program and other things are there. You can join it and you can learn the thing. Many of you, I believe, you aware this CST and HFSS, this thing, and the circuit validation we done over the EDS, which is the Keysight product. So the thing is, if I explain these things, so you can see here, this is the proposed structure actually. So initially what we did, you can consider this is a single element, correct? This is an antenna. correct? And if you check the frequency response, correct, of this system, so what you will find, this is operating at around 2.4 gigahertz. You can see the S parameters here, and from the S parameter, one can easily conclude that this is not a good mu antenna. Why? Because the thing is S21 is high here. We cannot use actually. So definitely we're supposed to come across some mechanism so that we can improve the isolation. Correct. So after that, what we have seen, if we remove some of the electrical length of this Minder line kind of shape, correct. So the same thing is actually working at near about 5.3 gigahertz. Correct. So the thing is, if you see carefully these two designs, correct. So what you find that changing the electrical length, you can manage your frequency of operation. Now this particular fact actually enable to use us these things. Pin diode means as a switch concept. If we want to place a switch, correct, in a suitable place, or if we make on or off situation, definitely I can toggle between 2.5 and between 2.5 and 5.3, correct. So either means making the on or off, we can get this frequency response or either this is frequency response. So this is one of the beauty of this structure actually, and how we did actually. I'm going to explain in the coming slide. So before that actually, let me explain that how to improve the isolation. So what we did actually, we fabricated two filters actually, correct. If you see the filter, this is again the Mender line based filter, and what we did, you can see this is a more or less same. What we did that here, if you see that some of the electrical parts we removed, correct. So you can see this structure. Now, if you see the S parameter here, so you can see that one filter, this is a stop band actually, correct. One filter is operating at 2.5, another is 5.3. So that is actually what we want. Now the idea is where should we place, correct. So for placement of this thing, we need to study the surface current, correct. We need to find that the origin of surface current and how the things are propagating in the structure, correct. So that by seeing these things, we can find some suitable location where we can use this filter to improve the isolation. So if you see here, this is the final structure, correct. So what you did actually, just between these two cell actually, two antenna cell, we place a filter actually. This is working at 2.3, whereas here also we place like this. And if you see, all the things are connected, correct. Uh, if you not connect, some of these things, S11 and other things will be degraded. So please try to connect this memo should be these things. All the images should be connected. If you're not connecting, sometimes you are not getting the proper response. But the thing is, you can still use that thing. But here we use the proper connections actually in all the element. So this is the surface current study, and this study tells here that if you see these things, these antenna, like if we let's say excited the port number 1, correct. So what you can see that here you can see some coupling, you can see here you can see coupling. Now what we did, we inserted this filter, correct, between these two elements. Now you can see the improved version. When you are exciting these antenna element and these antenna element, the very less influence, means there is no talking, as you can say, correct. So by incorporating this stop band filter, you stop those surface wave which reaches to these elements actually. So in this way we improve the isolation, correct. This is a fabricated one, and here you can see the top figure. You can see the yellow and black this thing. This is nothing but your pin diode. So we identified the location of the pin diode and we placed the pin diode. And finally, what we have, if you see the fabricated one, this is the fabricated antenna, correct. So so here you can see this is your top view, correct, and this is your bottom view, correct. Okay, so this between these two elements at the bottom side, we place this top one, correct. Okay, and these are the pin diode, these are the DC blocking capacitor, jumper wires, all the things we use to provide the proper biasing. It is important when we are using the active antennas. This is the setup actually for the biasing and the equivalent of the pin diode. These are the S parameter actually, if you see, correct. So finally, the thing is we got a very good response in terms of antenna parameter, ECC, and the parameters. All the things are in acceptable range, correct. So let's come to the CR, correct. Let's come to the CR because now we have the enough background to understand and implement these things with the cognitive radio, correct. So now so far we have seen the different MIMO parameters. We have seen that how the MIMO can improve uh, the data rates, correct. We have seen an example and how the diversity actually work to maintain the thing as well as the reliability and the data rate. So the thing is, these all the things we are still using, and your mobile is working at the LTE actually. These are the 4G, fourth generation technology, and this menu technology is used there, correct. Now the thing is, what is especially what actually we want to contribute and how these things will be. We are claiming that this will be used in our 5G, fifth generation communication, in sub 6 gigahertz, correct. So let us understand cognitive radio. So cognitive radio, this things, this is the intelligent spectrum sharing technique, correct. Okay, so with this respect, actually, our lab, correct, contributed the two antennas, correct. And you can see here, these are the features of the antenna, that this is a 4-port actually. For 5G communication, minimum 4-port is required, and over that you can go up to this 8 cross 8 and 12 cross 12, whatever you want. Actually, you can improve the reliability and this data rate, correct. At the same time, the complexity will increase, but we require the number of units, correct. Now, if you see the features, correct. So this is a 4-port antenna involving the combination of MIMO and CR technologies, and this is implemented this things mid band of 2.5 to 4.2 gigahertz, correct, which is the proposed one of sub 6 gigahertz. So the proposed system can exhibit both the spectrum interweave and the spectrum underweave cognitive radio functionalities. So the other novelty, if you're talking about the design, is the design uses the multifunctional filter. This is one of the challenging tasks here, correct? That how to incorporate this multifunctional filter. First, we have to design, then how to place with the antenna. This is another thing, because in a microwave, it is not like just placing the thing and the things are working. We have to find the suitable location. We have to find we have to do matching actually, so that we can properly match the system. Here, these things like the second structure, if you see, that the first one actually we just published in IEEE transaction and antenna propagation, correct, as a full paper, and then after almost the same concept but the different structure we developed and tested, but it offers the compactness as well as the tuning range, correct. So both the work concept wise is similar, but the second one has some extra advantages, but the working is almost same, correct. Now let us try to understand the cognitive radio. I hope you have seen the facts about the cognitive radio in textbook, correct. This has already been well explained. So this is proper intelligent spectrum sharing, I would say. So the thing is, here you can see the two pictures, correct. So we divided actually spectrum interweave or overlay, spectrum overlay and spectrum underlay, correct. So the thing is, first thing is that cognitive radio improves the spectrum efficiency of the system, correct. So in CR system, we have broadly two kind of schemes, as I told you. So like primary users, if I say the primary PU stand here, the primary users, which is a licensed user as well, who own the spectrum and can access anytime, and the secondary user, which is the unlicensed user, we designated as SU here, correct, who can utilize the spectrum when primary users are inactive, correct. And based on how the secondary user access the frequency spectrum, which is under the control of the primary user, correct. This is what, this is spectrum interweave or overlay, correct. Fine. So cognitive radio has been divided like these two things. So like if we talk about these things, interweave type these things, so it sense the spectrum first, correct, and by the tunable antenna, we can find the spectrum holes where the secondary users can work actually. And opposite to this, actually, if you see the spectrum underlay, correct. So here there must be some allowable interface level, correct. Means at the same time both the user can access the system, but secondary user should not communicate, because here the primary user transmitted power is below the. You can see here this is the interface level, correct. So here the power restriction is there, but we need to find it out the whole by using the wideband antenna. So the idea is there that we have to develop some of the antenna so that smartly these holes or these spectrum could be sensed. So the thing is, if I further explain these things, so if you talk about the requirements, correct, that how we can do, correct, in a hardware side from the antenna actually. So the wideband or ultra wideband antenna as a sensing antenna we have supposed to use. So the sensing antenna, this antenna scan the required frequency range and identify the spectrum holes, correct, which are not using by your primary user or licensed user, and a narrowband frequency tunable antenna as a communicating antenna you're supposed to build. Correct? These are all the requirement to make the cognitive radio system. What I'm trying to explain these things. So using communicating antenna, secondary or unlicensed user communicate over these spectrum holes. So overall spectrum efficiency could be improved in this way. Correct. So here the requirement is we require the two antennas. One is what? Wideband antenna, correct, which can sense the whole spectrum, and another is tunable antenna. Where you find the gap, you will communicate. Means who will communicate? The secondary user. Now, if you talk about the underlay, what are the requirements with the underlay? The requirements are here, the wideband or ultra wideband antenna as a sensing antenna, again we have to use, because we have to sense. Initially, we continuously we have to sense the whole spectrum actually. The sensing antenna scan the required frequency range and identify the primary user or license these things. Then after wide band with narrow frequency tunable band notch, here what? Band notch antenna as a communicating antenna will be required. So the secondary or unlicensed user communicate using these communicating antennas. So at whatever the frequency, the secondary users are creating interface to the primary user, or the secondary user transmits the power level, crosses the reference level. You can see these things. So what is set by the primary user, you can see this dotted line actually, correct. Then the secondary users stop their communication in that particular frequency band actually, or region, correct, using the band notch property of communicating, which we need to stop, correct. We need to stop working at. Are you getting this thing? Like what I'm trying to say, these two things are similar. The first point is similar, that both have the communicating antenna as a wideband antenna. Then after in overlay system or spectrum and interweave, we're supposed to use a tunable antenna. We're supposed to find it out, correct, with the place, the hole. And here in the underlay, we're supposed to find the minimum allowable interference level. If that is it is exceeded to that level, so from the band notch antenna, we can stop that place and the primary user will be working over there, correct. So this is the idea actually. Now, I would like to discuss here our one of the recent work, correct, which we published actually in IEEE Transactions recently, and this is the complete package, I would say, where we accommodated all the things. Like if I say that spectrum interweave and the spectrum underlay, both the things, the requirement is too much. Like we require the MIMO antenna, then we require the wideband antenna, then we require the band notch, these things, the response of the antenna, then tunable antenna. So 5 or 6 items are required. Now, if you try to accommodate all the things in the same place, definitely the size will be very much high. Correct. So what we did actually, we tried to accommodate the things with the help of this tunable, sorry, this multifunctional filter. Correct. So this, what is this multifunctional filter? This offers you the all possible combination. Like it can be act as a band pass, stop band, correct, or this band stop, correct. So all pass filter, sorry, all pass filter. So the thing is, these combination could be utilized with the help of this multi-purpose filter. So you have seen the different multi-band filter, correct, and band pass filter, correct, all pass filter. But now the thing is, we are trying to accommodate all the thing in a single packet. So a single unit of this MIMO antenna will carry the property of the wideband antenna, tunable antenna, band notch antenna, as well as all the multi-purpose filter response. Correct. So those 5 or 6 items we incorporated in a single item. Correct. This is one of the contribution from our side. Correct. So what are the design consideration actually? So here the technology involved, as I already told you, that this is a MIMO. Then after the frequency is 2.5 to 4.2. Then here we use the 4x4 element. And then after the isolation, we kept 15 and spectrum sensing technology as both. This is one of another actually the thing actually we achieved in a same platform. We try to have the spectrum interview and the spectrum underlay. Correct. Now, come to the design. Whatever I told you, I'm trying to show that how experimentally I validated these things. So here you can see this is a wideband antenna, the first figure, correct? This one. And if you see this, this things shape, this is a round shape antenna, correct? And this is a partial ground, correct? So the idea of the partial ground, we all antenna engineers know that the wideband response, as well as here, this is a smooth transition is there. If you see on the surface, so this also working with the wideband. So this is the wideband actually available. And this is working at 2.5 to 5.5, which is enough room we have to settle down this 5G application in between this. So the thing is, now we place the same antenna in this fashion, correct? And initially we tried to find it out its S parameter. Now if one can see the S parameter, so definitely that antenna person would not accept this design, because there is a lot of isolation. So the thing is, we supposed to find it out the proper isolation scheme, so that the structure will be not going to bulky, as well as we can easily find it out the isolation thing. Correct. So what we did actually, we use the reflector based isolator here. Correct. So we place a reflector here at the center, and what we found that if you see in this two figure actually, that if you are connecting like this, so earlier when there is a no reflector, so you can see there some power is coupled to the second antenna. But the moment you placing these things, sorry, the moment when you are placing the reflector at the middle point, correct, or between these two antenna element, you can see there is a no cross polar component, or there is no talking between these two antenna, and that is actually our objective is. Here you can see this is a multi-function filter development. So what we did actually, we use a very conventional unit cell, which is a splitting resonator, correct. And what we did, we tried to couple it capacitively, correct. So this is the equivalent circuit, and if you find the S parameter response, this is like that. Now what we did actually, we placed a vector diode at this location, and we provide a proper biasing. So here you can see we given 0, 2, 3 and up to 8. And what we find a very interesting result that we can tune this particular filter. This is S11, correct? This is your S11. So this band pass, this is a tunable band pass filter. So by placing this vector diode, we can do this thing. So one of the purposes is that we're supposed to get this tunable thing. So band pass filter, we're supposed to find it out. And now the thing is, if we are placing this vector diode, definitely we can tune the system like this. So this is the equivalent circuit and all the things. Now here, if you see this figure, so what we did actually, apart from this vector diode, we put it here. What? This is the pin diode, correct? This 4 location, correct? And what we found actually, if S1, we designated as S1, S2, S3, and S4. If all the switches are off, correct? So what you can see, this is the means we can tune the system as we see the previous graph actually. Now if this is on, correct? If this is on, so what will happen? There is a enough path actually to go the surface wave from easily from input port to through port, correct? And here you can see this is all pass filter. All the frequencies are passing. So this is the second requirement we passed, correct? Now the thing is, after that, because we need to provide the proper biasing and other things. So what we did actually, we provide the DC blocking capacitors here and all other things what we discussed. And here as a switch number 5, you can see here we inserted another pin diode, correct? Another pin diode. So what it actually is providing, if you see this thing, if S1, S2, S3 and S4, all these things are off, so this is all pass, correct? The same figure actually. And here if you see this S4 on and S5 is on, so S21 means this is what? This is the BRF, which is a band reject filter, correct? So this is the third requirement we completed from this thing. So now you can see placing smartly this pin diode and vector diode. A very simple structure could be used as a multi-purpose filter. This is all. This is the equivalent circuit you can consider where all the diodes, the placement, all the diodes you can easily see. Now, finally, the thing is, which is the challenging task for us, that how to integrate this antenna and filter. So what we did, we studied the perfectly. We tried to match the system, and we studied that how to place this multi-purpose filter at the feeding line, correct? So if you see this feeding line, so we incorporated this multi-purpose filter here, and this is the biasing line you can see, correct? So these are the measured these are the results actually. These are the simulated result. Finally, we put it here. So this is what this is your sensing antenna, which is a wideband antenna, and then after that. This B number is figure number B. If you see, this is an interview CR communicating antenna, correct? So you can tune, you can find. So for interview system, you can use a combination of this thing, and by placing the switches, these switches on or off. I have already told you. This is your summary. Actually, you can see. And here the third figure, if you see, this is for an underlay. So what you can see that at a particular point, this provides you the band reject response, correct? Band means it can provide the notch actually. So where the power level increases of secondary user, it and the requirement of the primary user is coming, so immediately it is stop the communication at this particular band by tuning these things. So in this way, what we can see that playing with the switches actually, now the same antenna, correct, integrated with the multi-purpose filter could be used as summary. Actually, you can see band. And here the third figure, if you see, this is a band filter or so what you can see that at a particular point, your tunable the antenna as well as your band notch band, correct? So these three provide the notch actually. Try to where the power level increases. So this is a fabricated structure, correct? And the requirement of the primary user is now. So immediately our challenge is how to stop the communication at this particular band by tuning complete. So in this way, what we can see circuit actually equivalent circuit diagram we studied over the years. Now, correct, the same, so you can see these things in our this integrated with the multi filter could be used as a band. And here the third figure, if you see, this is a band filter. So you what you can see that at a particular point, these are the measurable antenna as well as your band notch band. Correct. So these three are logically trying to where the power level is. So this is a fabricated structure and the requirement of the fabricator is now. So immediate challenge is stop to stop the communication and this is particular band by tuning complete. So in this way, what we can see that playing with the features now and the same you can see the conclusion integrated with the multi-color could be tunable and here the third figure you can see this is a so you want to get a particular point. These are the antenna as well as your background is correct. So these three are logically trying to where the power level is. So this is a fabricated structure and the requirement of the fabricator is now. So immediate challenge is stop to and after that what you have the one only complete. So in this way what we can see that again now and the same you can see the communicated with the multi-color if you want to do the play with the arrangement. So this is one of the arrangement. I'll not discuss all the results, but I would like to show the structure. This is the structure, and the same thing. And after that, we will perform here that first we design the bypass filter, then band notch filter, and then dash filter. So you can see, and this is a very simple mechanical and you can use the very simple play with the and then after this one of the array I will not use the bison in the results, but stuff like the diode and all the things correct in a single and the same thing is you see on the part that the signal so almost the same thing we got in this structure also, but here one of the important result we got that we save the size, means we miniaturize up to 48%. So half of the size actually we saved actually, and in this way that we claim the miniaturization. So you can see these things. This is just there is no rocket science you can say here. What we did, we just placed these antennas in a different way, correct? The first design what I have shown, that's a 4 antenna means on a substrate we just place at the corner. But here what we did some extra thing. We remove the middle part, correct, and the antenna structure itself providing some of the miniaturization and the filter also. And this is the arrangement we evolved actually, by which we are getting the small size, all these properties, correct. So in this way, from this designs actually, I would say that all the requirements we fulfilled what actually required for this we're still working over again that how to improve the game, because the thing is there are a lot of biasing lines. Wires are, you can see here, and when we are measuring in an echo chamber, so these plays a very important role. Means they are means acting as a new source and contributing as a cross polar component, and that is why this gain and all these things are reducing. So the thing is we are now trying to integrate the system and with the compact way, so that so that we can improve the gain and the efficiency, correct. So in our coming work, you will see that we are trying to improve the gain and radiation efficiency of the system, correct. So with this these are the comparison actually I made. So you can see the paper actually I have given all the things in a paper in a detail, correct. So for the values and the equivalent circuit particularly, correct. So Finally, these are the references we used actually, correct? And these are the two students actually. One is my PhD student, which is T. Srinath Reddy, and he's a PhD student. And one of my graduate student is Sanjeev Alam, who's worked and he published in AWPL. So with this, I would like to end this session and these things. And if any question you may ask, the session is open for the questions.
Thank you, sir. Now I request audiences to, if they have any questions, you can ask, sir.
Raghavendra sir, how can we find ECC on HFSD or CST, sir?
So the thing is, like I have already shown. If you check the formula, I have already given, correct. And in HFSS, you can easily get the S parameter. I would not recommend the S parameter. What you can do, the E theta and E phi, correct. This E theta and E phi means all the positive properties, and you embedded this formula and try to calculate from that. Otherwise, you can use the data. You can extract the data from the HFSS and you can use the MATLAB to get this. Yes.
Hello, good afternoon, sir.
Yes, good afternoon. Please tell me.
Sir, I have two doubts regarding reconfigurable antennas.
Okay.
One is, for example, we have two diodes in the design, and nothing but four possibilities are there, right?
Okay.
For example, I saw in one paper, IJMOT, in that paper, he used nearly 16 diodes, 16 pin diodes.
Okay.
So in that, the number of possibilities are 2 power 16 possibilities are there. But how to check, how to arrange or how to check the which diode is on condition and which diode is off condition?
Means I think you are talking about the biasing and other parts, these things.
Sir?
I think you are talking about how to do biasing and other things with the diodes.
Yes, sir.
So, like the thing is, what the diode we use, if you see the structure actually, that so many jumper wires and other things are there, correct? And for that, we use a DC blocking capacitor and all the things. We made a proper circuit, and then only we bias these diodes actually, correct? However, this is really very bulky when you bias a number of the diode. That is why I told you that we are still working that how to reduce this number of diodes actually, correct, and how to make the intelligent bias system or smart bias system so that we can improve the antenna gain as well, correct. So the thing is, so the thing is still means in a conventional way we are doing in the lab, correct, these wires.
Okay. Okay, sir. One more thing is how to fix the width and length of the diode in the design, sir.
You are talking about in simulation?
In simulation, sir. I am talking about the RLC.
Okay. So in simulation, what you can do simply, because this pin diode we are using for on or off condition, so you can non-model it, correct? You can non-model it and you can simulate the things, correct? This is one of the easy things. Yes.
Okay.
Good afternoon, sir.
Yeah, good afternoon.
Hello.
Yes, good afternoon. Please tell me.
Sir, what is the present MIMO configuration, sir?
Present MIMO configuration for 5G.
Yes, sir.
So far, I have seen the literature that minimum requirement is the 4x4, correct? But I believe this 4x4 will not going to help the things. So that is why we have to improve. We have to go further, like 8x or 8 or these things or other arrangements, correct? Because the reliability and the data rate is one of the area actually. That is why we are moving over the 5G, correct? Still, the things are we are using the in a LT system the MIMO technology. But the thing is, the new part is here that we are incorporating that how to get this intelligently. We can sense the spectrum and we can utilize the thing. So I would say the minimum requirement is 4x4, and beyond that you can go upside, correct, to improve that. But the system will be bulky, and we also develop actually 8x8 system in our lab, and soon you will see we'll publish this thing, and you can see that the systems are complex, but the thing is requirement is like that. And the other thing is that apart from when you are increasing this number of elements, at the same time the complexity is actually increased, and that is why system is also bulky. So other area is that how to miniaturize the thing. So those things we are still working at how to improve the gain and miniaturization. This is one of the area where you can also work.
Okay, sir. Thank you.
Yeah.
Raghavendra sir, in one of your circuits, you have used the reflector. It was of which material, sir?
Here I use the planar technology, and basically I use the Rogers substrate or FR4 substrate. And all this reflector, FSSS or bandpass filter, what I design over the microstrip technology, correct? So this is not a new material actually. I just have a small patch, correct? And that patch actually we analyze with the flocket port diagram, and we have seen it provide the proper the PEC response at those particular frequencies, and we place at the center that thing. So finally we have seen that due to this reflector, that the surface wave which is trying to reach to second antenna is going to back, and in this way we make the isolation actually low. Yes, please.
Hello. Good afternoon.
Hello. Good afternoon.
Good afternoon, sir.
Yes.
How to find power in the MIMO antenna, sir?
Okay, fine. Can you please? I'm not getting the voice.
How to find power in MIMO antennas?
Power.
How to How to find the power in MIMO antenna?
What power means you are talking about?
Different ports.
I'm not getting the question actually. What actually we want to ask?
While we are designing a MIMO antenna.
Correct.
For that one, how to find the powers? Suppose I want required S11 power or S12 power.
Okay.
How much amount of powers?
Okay, I got. I think this question is related with the measurements actually. That how to get the S parameters. Correct. Okay, that is no actually. Here we simply use a VNA, and when we are measuring a particular port S11 and S21, correct. So other ports we are matching with the 50 ohm distance, correct. In this way, what we did, we calculated all the S parameter by the help of vector network analyzer by matching the other ports. This is the things actually, and particularly when we are using this VNA, so normally that 0 dB actually. 0 dB the reference point, and with respect to that power we are measuring all the reflected waves.
Similarly, how to find the fidelity factor, sir? Fidelity factor for that MIMO antenna. How to find the fidelity factor?
I did not actually work on this.
Okay. Thank you, sir.
Thank you, sir.
Thank you.
Raghavendra sir, I'm Abdullah.
Hello.
Yes, madam. You can ask.
MIMO means we are taking multiple number of antennas. For that antennas, how much power is consumed by the antennas? How can we calculate that, sir?
If you are specifically asking about the power consumption actually or the power lost, so particularly when we are dealing with the antennas, correct. So all the antennas we are designing on the low power, correct. And in a lab actually we are measuring like S11 and S2 with the reference power level of what by default VNA is providing, which is 0 dB. Now the thing is losing the power, or the thing is with respect to antenna, we are measuring the gain and radiation efficiency of the antenna, correct? Or the ECC values actually. So by which actually we are saying how the antenna efficient, rather than calculating the individual power lost by the antenna. So what actually we are doing, we are finding the antenna parameter. So in this way we are analyzing. We are not straight away analyzing that how much loss in the particular antenna. But this is really a valid point that we supposed to find it out, the loss in particular antenna, correct, at the input side, and we supposed to calculate. So that particular things we are not actually, this practice is not we are performing in lab, but at the antenna side we are measuring all the parameters, particularly radiation efficiency and gain, to get the essence that how efficient is antenna is, correct? So we'll try these things. Very good point, valid point, correct. But most of the antenna engineers actually is not actually calculating this loss in power in individual units, correct?
Thank you, sir.
Thank you so much.
Raghuvinder sir, in cognitive radio, how can we distinguish the primary and secondary user in the context of antenna, sir?
Like the thing is with this design, okay, what I explained actually, we try to accommodate it here the multi-purpose filter, correct, and the antennas actually, correct. So as I told you, we try to accommodate all the things. Now we require a proper algorithm, correct, which is supposed to be done by the communication engineers, correct. As an antenna engineer, I have provided the tool that with the help of the biasing you can tune the system. Now we require a algorithm which is we are not actually doing in our lab, correct, but the antenna part actually we are doing, and which we are providing the flexibility to communication engineer so that he can write an algorithm so to sense the system. Like I said that we developed a wideband antenna or UVW antenna. So the thing is, there is a one dimension that the communication engineer first he will write the code and he will try to find it out the complete spectrum. Then after this tunable antenna, he will try to find it out what are the holes, correct. So this is done through the back algorithm which will be associated with the antennas, correct. So we are working on a particularly hardware side, correct. That software part, correct, we are not handling.
Sir, is there any standard literature is available for like insulation and kind of stuff?
Literature for what?
Sir, insulation, like you have used the insulation partner, like to reduce the S1 to S1 isolation. Sorry, sir. Yeah, isolation.
Yes. There is no particular book actually I have seen, but the thing is, I assure you, if you go through what paper actually I have explained, I have given the proper reference and proper methodology that how we will perform, because there is a 5 ways to do these things, correct. So in a lab, what we did, we particularly performed with the filters, we performed with the FSS, we performed with the reflectors, correct. So these 3 things we are doing these things with the MIHO. Other things, what you can do, you can check some of the papers, correct. There is no special book actually that how to means what are the methodology you will find, but I'll assure you, if you go to that paper, that IET map paper what I presented, then you will get a complete understanding that how we can improve the isolation. If you
Sir,
you mail me these things, I'll try to mail you the relevant things, correct.
Okay.
Okay, so hello,
Sir.
yes. So if there is no more question, then
Yes, sir. I think there are no more questions.
okay.
Thank you, sir. Thank you so much for being with us. Thank you for sparing your valuable time.
Thank you so much.
And thank you for being a part of this FDP. On behalf of our institute, I extend my gratitude to you. And,
Thank you.
Thank you so much, sir.
And one thing I would like to actually add here, that if any of the participants have some questions actually, so what you can do, you can give me my mail ID. You can write to me, and I'll try to answer over the mail.
Yes, sir. Sure, sir. You can share your mail ID, sir.
Yeah. Thank you. Thank you so much.
Thank you, sir. Okay, participants, tomorrow we will have day 3 session. The session timing and speaker details will be available by evening. Thank you so much for being part of this FDP. So we will meet tomorrow. I hope all of you have filled the feedback form.
Sir, where is the feedback form, sir?
It is already available in the chat window. Okay, if you are not
sir,
able
my chat window is empty.
No.
Excuse me, sir.
There may be a problem with your chat window. Just I again posted now. You see, can't you see the feedback link?
I'm unable to see, sir.
There may be a problem with
the chat window. The chat window also.
There is a chat window. See.
Yes. The beside participant chat window is there. And when opening chat window, it's clear only. No messages.
No, on your screen, can you see the symbols of raised hand, chat, and pupil symbol?
Yeah, only I seen participants and the chat window only.
Yeah, that chat window, if you click, what you are seeing? You are seeing nothing?
Nothing, sir. Empty, totally.
So you do one thing. You log into, I will send YouTube link here. You log into YouTube. There also, YouTube live is going on. There also, there is a feedback form. You can fill that feedback form there. Okay?
From YouTube, sir?
Yeah, from YouTube.
Okay, sir.
What about others? I think more than.
Otherwise, you do one thing.
Yes, sir.
What is your name?
My name is Rajendra, sir.
Rajendra. Okay. Are you in Telegram app?
Yes, sir.
Are you in the group, Telegram group?
Yes, I'm in Telegram group, sir.
Okay, in Telegram group, can you put your number now itself?
Yeah, okay, sir.
But we cannot write messages, sir. Administrator.
Yeah, sir. Only admin can write, no?
Okay, how many are facing this problem?
I am also facing, sir. I am not able to see the chat window also.
Sir, I am also facing the same problem, sir.
Yeah. Someone is raised. If someone is raised, everyone has to be.
Okay. See, in Telegram app there is YouTube link. Can you see?
Yes, sir. Through YouTube link, I open feedback form, sir. Okay, thank you, sir. It's there.
And in that link you fill.
Yeah, okay, sir. No problem. Thank you, sir.
So if anybody is facing to open chat window here, please go to Telegram app. There is YouTube link there. You click that YouTube link and then the YouTube link.
Sir, what about yesterday? Yesterday feedback I didn't give it.
Yesterday's feedback form is yesterday itself it was over. If you did not fill yesterday's feedback, don't worry about that, madam. You fill today's feedback.
Okay, sir.
Sir, can you please put the link in the Telegram app, sir?
Which link?
Feedback link.
No way.
No, how can I put in Telegram app if all 562 people will fill the feedback, right? There is a YouTube link in the Telegram app. You please go to the YouTube link, and in the YouTube link there is feedback form. Please fill the feedback. Okay. And that YouTube live will also close in 10 minutes. So you have to fill it now within 10 minutes. Okay.
Wait, sir. Please, sir.
Okay. Thank you. You can leave the meeting. I'm closing this meeting, sir. We will meet tomorrow. Thank you.
Okay. Thank you, sir.
वेट करते हैं भाई कहाँ बंदे मिलेंगे
ఈ ఛార్జింగ్ పెట్టమ్మా, ఛార్జింగ్ పెట్టు. ఛార్జింగ్ పెట్టా వేడే పెట్టు. ఏం హీరో ఆన్లైన్ క్లాసెస్ నీకు లేవా? మీ నాన్న ల్యాప్టాప్ కూడా ఇచ్చిందా? ఏది పనిచేస్తుంది. ఈ ల్యాప్టాప్ కూల్గా ఉండాలి కదా, ల్యాప్టాప్ వేడి కాకుండా కూల్గా ఉండాలి నీకు.